uh, we are dealing about the extensive and the intensive properties of a thermodynamic system. So if we are having some properties whose value is depending upon the quantity or the size of the matter that is present in the system. For example, if you see mass of a system or volume or internal energy, that is U, or enthalpy, that is H, or heat capacity that I'll discuss in the slide, that is capital C, then these things are called the extensive properties. But when we are dealing with such properties whose value does not depend on the quantity or the size of the system, then these are called the intensive properties. For example, density, that pressure, temperature, etc. These are called the intensive properties. So now, for example, if you take any extensive property, like that is called as chi, is a symbol in Greek alphabetical letter heads. So if we take an extensive property of chi and we have a number of moles of the matter present, that is n. So if we divide this chi by n, then it will form a new property that will be chi m, which is chi divided by n. Now this chi m will be a property which is intensive one, not an extensive one. The reason is quite simple, because the thing that is differentiating between extensive property and the intensive property is nothing but this number of moles, that is volume, or the amount, or the size of the system. Now, if we divide this extensive property by number of moles, that is n, we will form a new property which will not depend upon the number of moles. That's why chi m, which is chi divided by n, will be a new property which will be intensive one. Now, the same thing actually is valid for other extensive properties too. You see over here, volume is an extensive property. Now, if we divide this volume by number of moles of the gas present in the system, we have this new parameter which is Vm, which is molar volume. Or if we have this heat capacity, which is capital C, if we divide it by small n, and we get a new property which is Cm, which is molar heat capacity. Now both of these Vm and Cm will be intensive property. So any property P will be extensive, and that intensive properties will be their corresponding molar counterparts, which is Pm. So for any property, we have this, like for a property of P, which is extensive one. Now we will form an intensive property from the same just by dividing it by the number of moles present in the system. Another trivia can be here, like density, which is capital D, or it can be denoted by rho, this symbol rho. Now you know that density is nothing but mass by volume. Now, as you can see over here, mass, it is an extensive property, and volume, it is also an extensive property. But division of these two extensive properties yields us an intensive property, which is D, or density. So density is an intensive property. Its value does not depend on the amount of the matter present in the system. And M by V, both M and M are extensive properties. So if we divide an extensive property by another extensive property, we end up getting an intensive property, which is density, or D. Now molar volume, molar heat capacity, temperature, density, pressure. So here capital T, P, that is pressure of the system, all are the intensive properties. Now by an example, you will understand it far better. Look at this example. So we have a box. In the box, we have a gas confined, which is the volume of the chamber is capital V. Now, since gas occupies the entire box, we are having the volume of the gas also as capital V, and we have the temperature of the gas at capital T. Now, let's suppose we are separating, we are creating a compartment in between, so that there are two compartments. A boundary is created in between this, in between of the box. Now we have two halves, the half A and half B. Now at half A, the volume of the gas will be how much? If this was an homogeneous system and we are creating a separation in between, we are creating two halves. So in one half, the volume will be V by 2. And at this half also, the volume will be V by 2. But the gas temperature will not be T by 2 over here. The gas temperature here will be T. At this part also, it will be T. So you see the temperature, which is capital T, its value does not depend upon the amount of gas present in the system, but the amount, that is volume or capital V, its value depends upon the each half of the, or the amount of the system. So as you can say, not only in two, you can go on with n number of compartments over here. If you separate, if you create some n partitions over here, n number of partitions over here, and then we will be seeing each of the partition compartment has a gas volume of V by N, which is nothing but, which will be V by N. And at each compartment, the temperature will remain as T. It will not be T by N. It will not be T by N, but at each compartment, the amount of the gas will be capital V by N. So I hope here we have got a brief idea about the extensive and the intensive properties, because in thermodynamics, we'll be dealing up with these kinds of properties very frequently. Pressure, volume, temperature, density, or enthalpy. These things are very trivial thermodynamics, and depending upon the nature of the property, we can separate these two between extensive bond and the intensive bonds. In examination, we will be coming up with different kinds of examples will be given to you, and they'll ask you which are the intensive bond and which are the extensive bond. If you are given these properties like molar volume V bar, so molar volume can also be symbolized as Vm or V bar. So if you are given these properties V bar, P, T, H, and D, that is density, and they will ask you, please tick which are the intensive properties and which are the extensive properties. So the answers will be very much easy if you have gone through this slide. It will be D, density, and V bar, which is molar volume. These two will be intensive properties. And the rest of the things that are P, that is pressure, T, that is temperature, and enthalpy is H. These three properties are extensive ones. Now we will come to the concept of heat capacity and specific heat. So while beginning our class, I have told you in this class we will learn about a new parameter which is very important in thermodynamics, which is heat capacity, and it is denoted by capital C. There will be many suffixes here like X. X will be P or V. Now, whichever suffix is there in case of heat capacity, you will be understanding the fact that at that constant value, the heat capacity will be calculated. So if it is Cp, it means heat capacity at constant pressure. And if it is Cv, we will be taking up it as Cv, which is the heat capacity at constant volume. So now we're talking about the heat capacity. I'll start with two examples for easy understanding. Now, suppose we have two different kinds of beakers. One is a beaker which has 100 ml of water, and we have another beaker which has 20 ml of water. Now, both of the beakers have different amounts of water present in it. One has 100 ml and the other one has 20 ml. And both of them are kept at a temperature of capital T. Now, they are subjected to same input of heat energy. So, both are actually heated up by a Bunsen burner at the same temperature. Suppose it is 60 degrees Celsius. So, at 60 degrees Celsius, we are heating both the beakers at a, and they were both kept at a safe temperature. Now, which one as the 20 ml of water, it will experience more rise in temperature very quickly. You will see that is 20 ml of the beaker that is containing 20 ml of water. This beaker will be heated up to 60 degrees Celsius under at 5 minutes. Suppose. But in case you will be seeing that within that 5 minutes of time, the temperature of this beaker will be only 40 degrees Celsius. And its temperature by that time will be reaching 60 degrees Celsius. So this will take up heat much more faster than this one. It is also, you will see this very important, and you will see this very much frequently in your daily life also. If you can do this experience at your home, like you have two different glasses, one has 10 ml of water and the other has 50 ml of water, and then we will heat up both of them simultaneously. We will see that the glass which is having 10 ml of water will be heated more rapidly than the one which has 50 ml of water. Now, heat capacity, here comes the concept of heat capacity. The heat capacity of an object depends on both of its mass and its chemical composition too. And because of the larger mass or the larger amount of compound that is present in the larger beaker, then this large beaker will have a larger heat capacity than the smaller one. So we in this, by this heat capacity over here, we will try to calculate or measure the heat transfer to a system. The heat that is heat that is producing or heat that is taken up by the system will result in a rise in temperature when heat is absorbed by the system. Now, the increase of temperature is proportional to the heat that is transferred. The heat transferred, if it is Q, because in thermodynamics heat is denoted by Q. So the Q will be some coefficient multiplied by delta T, that is change in temperature. Now, the increase of temperature is proportional to the heat transferred. Now, this, if you see Q, that is heat transferred, and it is the delta T, it is the transferred, the increased temperature. So Q is actually directly proportional to capital T. So if we leave this proportional sign, you will bring a constant which is a coefficient, which is Q equal to T into delta T. So we have this equation, Q is equal to C into delta T. Where C is the heat capacity. The magnitude of this heat capacity, or C, that is the coefficient, it depends upon the size of the system, the nature, and also the composition of the system. And this C is called the heat capacity. So we can measure the heat supplied just by monitoring the rise in temperature, provided that is we know about the heat capacity. So we can calculate or measure the delta T by dipping a thermometer inside the system. And if we have a knowledge about the heat capacity or C of the system, we can readily calculate Q, that is heat transfer to the system. So when C is large, a given amount of heat results in only a small temperature rise. Because if you see, C is a constant, capacity is a constant, which is measured by Q divided by delta T. Now, if C is large, so that means Q by delta T will be very much high. So here is a thing that will be understandable by you and is very important for you to understand, like which kinds of compounds have higher heat capacities. We have this C as a fraction. These fractions in numerator we have Q and in denominator we have delta T. Suppose a compound has a very high heat capacity. So is quite large. So if C is quite large, we say if Q is high, a given amount of heat, that will result in a very small temperature rise because we have the fraction as Q by delta T. Now we have this Q, that is some amount of heat that is transferred to the system. Now to make this fraction larger, because we have seen that we have said C is quite large. So to make this entire fraction large, either the denominator should be low or the numerator should be high. So if for a specific amount of Q, that is heat transferred to the system, delta T will be very much less to make the entire fraction larger. So this is very much frequent in our daily life because the liquid that we encounter, that is water, most in our daily life has a very high heat capacity. It is has a very high heat capacity. So since it is having a very high heat capacity value, so very high amount of energy is required to raise this temperature. So in case of water, you can see the specific heats are actually given. The specific heat definition of a substance is the amount of energy that is required to raise the temperature of 1 gram of the substance by 1 degree Celsius. It is the definition of specific heat. And we have actually listed the specific heats of the below substances. The symbol for specific heat is Cp, but the P subscript is referring to the fact that specific heats are measured at a constant pressure. So whichever will be given as a subscript, it will be constant for this measurement. So Cp means specific heat at a constant pressure and Cv means specific heat at a constant volume. So you see C is Q by delta T, and since for a given C, if C is large, so for maintaining the high fraction, delta T will be very much low to make the fraction larger. Since water has a very high C or the heat capacity value, a specific heat capacity, we have to know that a very high amount of energy is required to raise this temperature. So very much larger amount of heat will result in a very small temperature rise. So here the lists are given. Water liquid form specific heat is 4.18 joule per gram per degree Celsius. Water solids, that is ice, it is 2.06. Water in gaseous phase, that is water vapor, has a specific heat of 1.87. So in the liquid form of water, the specific heat is highest. So water in solid state, that is ice, have a 2.06. Ammonia in gaseous form has a heat capacity of 2.09. Ethanol has 2.44. Aluminium in solid state has 0.897, which is very low heat capacity. Carbon, that is graphite, has even lower, which is 0.0709. And the 3D metal, which is copper, in its solid state, has a heat capacity of, it is very much low, which is 0.385. So it is almost 10 times or 12 times lesser than water in liquid form. Now, C is actually directly proportional to the amount of substance, and that's why C is an extensive property, as I have told you in the last slide. But the molar heat capacity, which is Cm, so if we divide C by N, that is number of moles, if we have Cm, which is C by N, which is the heat capacity for a mole of a substance, in that case, it is the quantity of heat needed to raise the temperature of 1 mole of the substance by 1 degree Celsius or by 1 Kelvin. Specific heat, also called the specific heat capacity, these two terms are interconvertible and they can be used concurrently, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius or by 1 Kelvin. The specific heat can either be expressed in joules per grams per degree, or it can be calories per gram per degree. So 1 calorie and joules are interconvertible because 1 calorie is approximately 4.18 joules. So for finding out the heat Q, which is required to raise the temperature of a sample, we have to multiply the specific heat of the substance by the mass of the substance by the temperature change. So we have Q, we have to calculate Q, which is heat required to raise the temperature of a sample. If we have the molar heat capacity, which is C of the substance, which is small c, multiplied by the mass of the substance, which is small m, multiplied by delta T, which is change in temperature. So here it is small c with specific heat of molar, and the mass, if we multiply small c into m, we are dealing with the specific heat capacity, which is capital C into delta T. So now we have got a very brief idea about QC and T, how they are related. Now we will be talking about the relationship between these two parameters, which is Cp and Cv. So heat capacity at constant pressure and the heat capacity at constant volume of an ideal gas. Now the heat capacity Q is noted by C into delta T, as we have known. The coefficient, that is C, it depends upon the size, composition, and the nature of the substance. The relationship between Cp and Cv for an ideal gas will be considered over here. Ideal gas are taken because for ideal gas, there is a very easy combination between Cp and Cv, which is the equation between ideal gas is Pv is equal to inert T. If we take up a van der Waals gas, so for case of van der Waals gas, we have this very complicated equation, P plus A n square V square into V minus NV into RT. So for our easy understanding, we will be talking about the ideal gas system. This is a van der Waals gas equation, which is a bit complex. But in case of this, the ideal gas, the equation is Pv equal to inert T. Since this equation is much simpler, we will be taking this for our easy calculation. The relationship between Cp and Cv for an ideal gas is there. Cp is heat capacity at constant pressure, as I have told. The suffix or the subscript stands for that at a constant value. and CV is the.
I didn't catch that. Could you try again?
So now we are dealing with two different equations, which is Cp and Cv. Now, in the first case, we have a QV, that is heat transferred at a constant volume, QV. So QV will be Cv into delta T for a temperature change of del T. And we have this temperature change or the heat absorbed, that is QP, at a constant pressure as Cp into delta T. As you have know that Cv into delta T is nothing but delta U, that is change in the internal energy, and Qp, which is Cp into delta T, is equal to delta H, that is change in enthalpy. So from these two equations, we are getting the new equation, which is Cv is equal to delta U by delta T, which is equation 1, and Cp as delta H by delta T, which is equation 2. So what will be happening now? We have two different sets of equations, which is Cp and Cv. So if we subtract equation 1 from equation 2, we have Cp minus Cv will be delta H by delta T minus delta U by delta T. So we'll take delta T in the denominator as common, and on the numerator side, we have delta H minus delta U. Now, from the last class, I have shown that delta H is equal to delta U plus nR into delta T. So, from this equation, we have if delta H is equal to delta U plus nR delta T, then delta H minus delta U will be nR delta T. So, we'll substitute delta H minus delta Q as nR delta T on the numerator. Now, we'll be having Cp minus Cv equal to nR delta T by capital delta T. So this delta T will be cancelled out, and we'll end up getting Cp minus Cv as nR, or Cp bar minus Cv bar will be R, where Cp bar is equal to Cp by N, that is the molar heat capacity, and Cv bar will be Cv by N, which is also the molar heat capacity at constant volume. So this is the relationship between Cp and Cv, or Cp bar minus Cv bar. So Cp minus Cv will be nR, or Cp bar minus Cv bar is equal to the molar gas constant. Now we are introducing a new term, which is gamma over here, which is defined by the ratio of Cp and Cv. So if we have a ratio of the molar heat capacity at constant volume and the molar heat capacity of the constant pressure and the constant volume, we have this ratio as gamma. So this gamma is defined by Cp by Cv, or Cp bar by Cv bar. Since Cp is equal to Cp by N, Cp bar equal to Cp by N, and Cv bar is equal to Cv by N. So both of the molar heat capacity ratio and the normal heat capacity ratio gives us gamma. So now we have the equation Cp bar minus Cv bar as R. Now if we divide both sides of this equation by Cv bar, we have this Cp bar by Cv bar minus 1 is equal to R by Cv bar. Now Cp bar by Cv bar is termed as gamma. So R by Cv bar is gamma minus 1. So if we rearrange this equation, we have Cv bar is equal to R by gamma minus 1, which is corollary 1. And the second corollary comes is Cp bar. Cp bar is Cv bar plus R from this equation. So R plus, we will substitute the value of Cv bar over here as R by gamma minus 1. If you can take R as common from these two terms, we have 1 plus 1 by gamma minus 1. By solving this equation, we will have gamma over here. So Cp bar will be R into gamma by gamma minus 1. And Cv bar is equal to R into 1 by gamma minus 1. So R by gamma minus 1 is common in both Cp bar and Cv bar. So if we divide Cp bar by Cv bar over here, we will see that this R by gamma minus 1 terms gets cancelled out and we end up having gamma. So Cp bar by Cv bar will be gamma. So there are some numerical problems that will be solved for here that are we are discussing for the thermodynamics chapter. So here the problem is calculate the Q, delta W, delta U, and delta H for the reversible isothermal expansion of 1 mole of an ideal gas at 127 degrees Celsius from a volume of 10 dm cube to 20 dm cube. Now, if we are talking about an ideal gas, for an ideal gas, if the process is isothermal, so the change in temperature of the ideal gas is 0. For an isothermal process, delta T is equal to 0. And since it is an ideal gas, we know if the process is isothermal, then delta U will be 0. The change in internal energy will be 0. And also, if we are calculating delta H, that is change in enthalpy, the change in enthalpy of the gas. So delta H is equal to delta U plus delta of PV. That is the isothermal work done. In the pressure corresponding term, delta Ng T. So also in this case, we have this PV term over here. Delta PV means R into delta T. So delta H is equal to delta U plus delta of inert T. Now inert is a constant. So we are having delta H is equal to delta U plus inert into delta T. Now since for an ideal gas and also an isothermal process, this delta T terms is equal to 0. So delta H is equal to delta U. So if delta U is 0, delta H is also 0. So for a isothermal process, we see that the delta U and the delta H for this ideal gas will be 0. Now from the first law of thermodynamics, we know delta U is equal to U plus W. Now we have already obtained that delta U is equal to 0. So Q is equal to minus of W. Now how we can calculate the W? So we have seen that for W calculation in a reversible process, we have this equation W is equal to minus in RT ln of V2 by V1. So either this form can be useful, or if we put out the ln to log, we will have minus 2.303 in RT into log of V2 by V1. So here we have this n as 1 because it is said that number of moles is 1. N is equal to 1. The temperature is capital T, but it will be not required here because in none of the calculations, temperature is actually required. So temperature is 127 degrees Celsius. So it is 127 plus 273. This much of Kelvin. This 400 Kelvin. We have this R as 8.314 in joules per mole per Kelvin, and the temperature 400 Kelvin is also here, and we have this ln of V2 by V1. So V2 is 20 dm3 and V1 is 10 dm3. Since pressure and volumes are inversely proportional, so instead of volume, you are given the pressure, then the equation will be a bit different. So we see PV is constant. So P1 V1 is equal to P2 V2. So if we have V2 by V1 over here, if we can express this in terms of pressure, it will be P1 by P2. So if instead of volume pressure is given, we will denote this V2 by V1 as P1 by P2. So now we are getting the work done as minus 2.3 either in the equation or in this equation, minus of nRT ln V2 by V1. N is 1, R is 8.314 joule per mole per Kelvin. That is the molar gas constant. T is 400 Kelvin. So finally we have ln of V2 by V1, which is 20 by 10, which is 2. So finally we have got the equation, and from by solving these numerics, we'll have W is equal to minus 2.305.3 joule. That is work done by the system. And the amount of Q, which is minus W, will be the heat absorbed by the system, because Q is just the negative value of W. So Q will be just the positive value, 2.2305.3 joule. That is heat absorbed by the system. We move to our next numerics, which is as calculate the work done when 2 moles of an ideal gas expands reversibly and isothermally from a volume of 500 ml to a volume of 2 liters at 25 degrees Celsius and at a constant normal pressure. So we have N is equal to 2 moles. Now V1, that is the initial volume, which is 500 ml, that is 0.5 liter. Since we are dealing with V2 by V1, so both V2 by V2 and V1 should be of a same unit. So that's why this V2 is expressed in terms of V1 and V2 both are expressed in terms of liter. So V1 is 0.5 liter and V2 is 2 liter. So we have V2 by V1 as 2 by 0.5. That is equal to 4. Because it is 2 by 0.5, that is 4. The temperature is 25 degrees Celsius, so it is 298 Kelvin. And N is given as 2. Now W is equal to minus 2.303 nRT log of V2 by V1. So we have all the parameters value present over here. So we have W is equal to minus 2.303 into 2, that is N number of moles, multiplied by R, which is 8.314 into 298, the temperature, and log of V2 by V1, that is 4. So by solving this, we have this work done value as minus 6871 joules. If we have to convert this value to kilojoule, we write it as minus 6.871 kilojoule. But if we have to consider it in a kilojoule format, also we have this calorie and other terms also. One calorie is approximately equal to 4.184 joule. and 1 liter atmosphere is approximately 101.3 joule. So 1 liter atmosphere is much higher than 1 calorie. So 1 liter atmosphere by 1 calorie is 101.3 divided by 4.184. So if we perform the division, we have that is approximately 24.2. So 1 liter atmosphere is approximately equal to 24.2 calorie. So these are different ways of expressing the amount of work done. One is joule or kilojoule, and another one is the calorie or kilocalorie. The other one is 1 liter atmosphere. So we have these three sections or for interconversion between calorie and joule. 1 calorie is this much, 4.18. 1 liter atmosphere is 101.3 joule. And if we divide between these two, we get the relationship between liter atmosphere and calorie, which is 24.2 joule. So whenever you are talking about which will be easier for you to denote, for R value, we have 8.314 joule per mole per Kelvin. So R is 8.314 joule per mole per Kelvin. If we divide this 8.314 value by 4.184, we get this R value in calorie, which is 1.987 calorie per mole per Kelvin. So it depends upon which kinds of R we are using. If we use R as 8.314 joule per mole per Kelvin, we will be having the value of joule. If we use the R value in calorie, we will have the ultimate energy value in calorie. So likewise, liter atmosphere also, we are having an R value. So 1 liter atmosphere is approximately equal to 101.3 joule. So if we have to convert the R value in liter atmosphere value, will we have to divide 8.314 divided by 101.3. So then we will have the R value in liter atmosphere will be 0.082 liter atmosphere per mole per Kelvin. This per mole and per Kelvin will be cancelled out and we'll end up getting R as the work done value. So to calculate work done value, we can easily use any of the R values either in joule or in calorie or in liter atmosphere. So depending upon which R we are using, ultimately we will get the work done value. The work done value will be joule, and ultimately if we use this R value, it will be in calorie if we use this calorific R value, and if we use this liter atmosphere R value, we will be dealing with the ultimately the liter atmosphere. But then if we have to calculate, if we are having this delta U equal to Q plus W. Now if we have to calculate, we are given two different kinds of W's. One is Q, another is W. If you are given the Q value as 100 calorie, and we are performing the W in joule. Then after calculation of W in joule, you have to convert it in calorie, and then you have to again to add it to the Q value. So you have to look after which amount of work it is given already. So better you will use that R value only. If the Q value is given in calorie, you will start calculating W value in calorie from the very first step. So that ultimately we have got the W value in calorie, and then we will add this to Q and W to get the ultimately delta U value. So I guess here there is an easy understanding of the work done of the system. In this case, here I have also come up with another example for your understanding of this numeric. Here we will have to get the work done for N is equal to 0.75 moles of an ideal gas. So N will be 0.75 moles of an ideal gas. It is also an isothermal expansion, and it will be an ideal gas. So for an isothermal expansion, the volume of the gas expands from 15 liters to 25 liters. The temperature is reversible at 27 degrees Celsius. So the capital T will be 300 Kelvin. Now, what will be the work done in this case? W, we will use the equation for the reversible maximum work, which is W is equal to nRT ln V2 by V1. So N will be minus N will be 0.75. R, we can use R either in joule or in calorie. So now we will use it in joule, 8.314. Capital T will be 300, the temperature in Kelvin. And we have ln V2 by V1. V2 is 25 and V1 is 15. So it will be 5 by 3. So if we calculate it, we'll have the value as minus around 955 joule. That is the amount of the work done by the gas. Likewise, by using this equation, W is equal to minus nRT ln V2 by V1, we can solve different numerics of thermodynamics. In our next class, we will be talking about different enthalpy of formation, different kinds of enthalpy that are present in this system, and how we can physically calculate the enthalpy of a system. And there will be reaction enthalpy, there will be enthalpy of sublimation or enthalpy of evaporation. So these kinds of different enthalpy parameters we will discuss. So if you have any question regarding any of the slides, you can ask to clarify your doubts.